Hi, my name is Moulik Gaglani and welcome to my video on what an ALU is. I'll be going over the function of the ALU and my journey on building the ALU circuit. What is an ALU? An ALU is short for Arithmetic Logic Unit. It is a digital circuit that performs all arithmetic computations such as addition, subtraction, multiplication, and division. It also performs logic comparisons such as mostly but not limited to and, or, and not. The ALU is the fundamental building block of the central processing unit, also known as the CPU, inside a computer system. All information used and stored by digital circuits, in this case the ALU, is in binary numbers, which are 0 for logic low and 1 for logic high. Inputs and outputs flow through electrical paths called buses. Now, in the ALU circuit that was to be built for the project, there are two input data buses, one 3-bit data bus A and the other one is a 3-bit data bus B. Also in the ALU, there are places called registers which store information. I have two registers in my circuit, one 3-bit register for one of the input data buses and one 4-bit register for the outputs, which is also acting as a register for the input data bus A. Now the final result after the execution of any operation has to be stored somewhere. This data, this information, is stored in a place called the accumulator, which is the same as the register for the outputs. The flow of bits and operations to be carried out is controlled by gated circuits. Specific arrangement of these gated circuits means that specific operations can be performed by the ALU. In the circuit that was to be built for the project, we were using one half adder and two full adders. This allows the particular ALU circuit to perform addition. Let's move on to the specifics of my ALU circuit. The circuit is being used as a memory circuit, which takes use of the commercial D flip-flop circuit, which is a synchronous sequential circuit. These D flip-flops have a positively edge-triggered clock pulse, which means that the output in the registers only changes the instant moment the clock changes to a logic high. In this case, the clock is positively edge-triggered but has been inversed by the AND gates, which means that the output in the register only changes the moment the clock receives a logic low, a 0. The section of the circuit that is doing the adding is the combinational circuit. The gates are arranged in adders so that they can add inputs A and inputs B together. Now let's take a look at the circuit itself. When we power on the circuit, we can see that the LEDs and the registers are on. We can turn the LEDs off by overriding the outputs of the commercial D flip-flops. This is done by connecting all the reset pins to a button. When the button is pressed, the reset pins will clear and override all the cues, the outputs of the commercial D flip-flops, hence turning the LEDs off. The buttons are connected in a voltage divider with the resistors being used as pull-up resistors, meaning that the clear pins will always receive a logic high when the button is not pressed. If the button is pressed, the clear pins will read a logic low, which will override the cues. All the inputs used in the data buses are connected in a dip switch, which is also connected in a voltage divider with the resistors acting as a pull-down resistors. This means that the inputs will always receive a logic low unless the switch has been activated. There are also two more inputs on the dip switch, load enable and add enable. The task of the load enable input is to write any inputs to the register, loading the inputs into memory. The task of the add enable is to add the input A's to the input B's. Input A stays static, and it is the input B's that get added to the input A's. There is also a button that is used after the load and the add have been enabled. The task of this button is to actually load the inputs to the register. The button is connected to a Schmitt trigger. The task of the Schmitt trigger is to reduce the voltage debounce that occurs when the button is pressed and released very quickly. The voltage debounce occurs due to the fact that there are two very close metal plates inside the button that bounce off against each other when the button has been pressed and released. To add values, simply load the inputs first, then turn off the load as the input A's will stay in the accumulator as if they're being loaded for the first time. Let's say that A0 is turned on and B0 is turned on. Load enable and add enabled both turn on will give you the following values in binary: 1, 1. This is like saying the answer to 1 plus 1 equals to 2, 1, where 2 is the actual sum and 1 is the memory holder for the input A. This is the reason why we have to turn the load enable off before adding the inputs together. Moving on, I would like to reflect upon my process of building the circuit. I strongly believe that I could have done much better and that this project was not my strongest performance by far. I think that the reasoning behind the poor performance by me was due to time management problems. I had followed the Gantt chart timeline up until the building section. I fell behind after missing the first build day and not getting much done during the long weekend, because I had misjudged the time that would be required for me to build and test the circuit properly. After falling behind the first build day, the situation got worse by each day as I was trying to catch up the missing days. I could improve by managing my time wisely and putting a little extra time into circuit projects, as they should have at least 1 or 2 days kept aside for testing and troubleshooting. This concludes my video about the ALU circuit. Thank you for watching.